All right, everyone, welcome. Today we're going to go over our Day 1 notes for Unit 13. So this unit, we're going to be focused on inverse trig functions and their relationships. Last unit, we talked about sine, cosine, tangent, secant, cosecant, cotangent, all of our trig functions plus our reciprocal functions. Specifically, when we talk about inverse trig relationships, there's a couple of things that we have to keep in mind. In order for a function to have an inverse, we know that functions must be one-to-one. So I'm just going to make a little note of that at the top. So in order for a function to have an inverse, functions must be 1-to-1. Just like we can test whether a function actually exists or not with the vertical line test, we can use the horizontal line test to determine whether a function is indeed a one-to-one function. Now, as I draw a horizontal line here through the sine function or through the cosine function, we'll see that it intersects the function's curve multiple times, meaning that function is not one-to-one. And if you think back to kind of partway through first semester, we talked a lot about inverses, and we made that connection of how a function and its inverse are reflections of each other across the line y equals x. And if a function is not one-to-one, meaning it doesn't have one unique input for each output, then we have to restrict the domain. So you'll see for sine and cosine here that we've got a box from negative pi over 2 to positive pi over 2. So if I were to trace just this part of the curve, okay, I'm able to restrict the domain of sine to negative pi over 2 to positive pi over 2. Now, as we continue to graph this function, it oscillates back and forth between -1 and +1. We generate all the same function values, but the highlighted portion here would be considered one-to-one and would pass the horizontal line test. With cosine, we have it restricted from 0 to pi. And you'll see that if we restrict it to 0 to pi, that we have another section of the function that passes the horizontal line test. You'll see that over here on the right side, cosine x is this curve that we have right here. And we have a little bit more graphed than what's necessary. We're going to focus from 0 to pi for cosine. That's the part that gives us a one-to-one function. You'll notice that when we take a look at the inverse for cosine, that the domain before was 0 to pi for cosine, if we're just looking on that interval. You'll notice that the range for our cosine inverse is now 0 to pi, because remember, our domain and range flip when we create that inverse function. So you'll see that we have arc sine, arc cosine. That's another way of saying the inverse of sine. Another common notation you'll see is sine inverse of x, and we'll use that -1 to provide the notation for the inverse. So rather than saying arc cosine, you might also see it as cosine inverse of x. So moving on to the tangent function, and I'm giving you the domain in which you will always be restricting it. Tangent, we're always going to restrict from negative pi over 2 to positive pi over 2. And we're going to go ahead and we're going to have parentheses because we have vertical asymptotes there. Our cosine inverse function will always be restricted to 0 to pi. And then sine inverse or arc sine will always be negative pi over 2 to positive pi over 2. Yes, there are different intervals that we can use to create a one-to-one function. I'm giving you the intervals that you are going to use for evaluating our inverse functions. Cotangent inverse, we are going to restrict from 0 to pi, so just think between our asymptotes. So cotangent inverse of x, we're going to be restricting to 0 to pi with parentheses. Secant is the reciprocal of cosine. So again, we're looking at that same window that we did for cosine from 0 to pi. But with secant inverse, it's going to be 0 to pi over 2 union pi over 2 to pi, because we have to keep in mind that with secant and cosecant, we also have vertical asymptotes that are going to take place there. So that's not going to be a smooth curve from 0 to pi. We're going to have an asymptote halfway in between. Same with cosecant. We're looking from negative pi over 2 to pi over 2, but we have that asymptote at 0. So 0 will not be included in our inverse options for cosecant. So we're going to get into evaluating our trig functions, and the biggest thing here to keep in mind is what the inverse function does. So I tried getting to restricting the domains, the different windows that we're looking at, and getting that kind of out of the way first so you can mark up your notes. The things to keep in mind, I'll write this down here at the bottom, is that if we were to evaluate a sine function, for example, radians goes in and a ratio of sides comes out. So anytime we put in a radian measure, a ratio of the sides of the reference triangle is what comes out. So if it's sine of pi over 6, and the ratio of the sides there is 1/2. We're in quadrant 1, the opposite side is 1, hypotenuse 2, this side is root 3, opposite over hypotenuse, sine of pi over 6 is equal to 1/2. If we take the inverse function, then a ratio of sides goes into the function, because remember, inverses, we're flipping the input and the output. What comes out is our measure in radians. So normal trig function, radians goes in, ratio of sides comes out. Inverse function, ratio of sides goes in, radians comes out. We are just flipping our input and output. So if I were to give you sine of pi over 4, we would all say that that is 1 over root 2. Triangle, quadrant 1, 1, 1, root 2. But when I give you the inverse function, I might say sine inverse of root 3 over 2. Well, where does that triangle fall? That triangle is in quadrant 1, where the opposite side is root 3. A hypotenuse is 2. This side would be 1. What is this radian measure? Pi over 3. So we're working backwards from before, where we would put in the radians. You would tell me the ratio of sides given the unit circle. Now you draw your reference triangle in the given quadrant, and then give me the radian measure that corresponds to that reference triangle. So when we have cosine inverse of 1, cosine of 1, think about this if we're evaluating just a regular trig function, cosine of theta is equal to 1. What values of theta are we looking for? If you think about drawing your cosine curve, here's cosine. But remember, we're talking about the inverse function. We are only looking from 0 to pi. When is cosine of theta 1? At 0 radians. Theta equals 0. So simply, cosine inverse of 1 is 0. Think about our ordered pair. Now the output goes in. The previous input is what comes out. Sine inverse of negative 1. Let's go ahead and draw our sine curve. Remember, we're only looking from negative pi over 2 to positive pi over 2 for the inverse sine function. Because remember, our function at the end of the day has to be 1 to 1. So we restrict the domain. Sine is always going to be negative pi over 2 to positive pi over 2. Where's that? Where's sine inverse of negative 1? Well, that would be right down here. That would be at negative pi over 2. I don't have to draw my reference triangle because these are my quadrantals, the ones that fall at pi over 2, pi, 3 pi over 2, and 2 pi. This ordered pair would be negative pi over 2, negative 1. We are just flipping the ordered pairs. So the ones that are actually going to involve the unit circle that fall in between our quadrantals, Arc sine, so we know that we are looking at quadrants 1 and 4, to positive pi over 2 and to negative pi over 2. Where is sine negative? Sine is negative in the fourth quadrant. Yes, it's negative over here. It's actually positive, sorry, in quadrant 2, but it's negative in quadrant 3. But remember, we are just looking from negative pi over 2 to positive pi over 2. So I'm going to draw my reference triangle where the opposite side is negative root 3. Here's 2. Here's 1. What is this angle of rotation? Negative pi over 3. So ratio of sides goes in. A radian measure comes out. Sure, we could also write this as 5 pi over 3, but remember we are restricting our domain to fall between negative pi over 2 and pi over 2, so we are just looking at quadrants 1 and 4. 5 pi over 3 is the same as negative pi over 3, but negative pi over 3 falls within our window. I'm going to allow you guys to fill out the next 3. I'll show the solutions, and then you can start your practice for today. All right, your next 3 solutions for secant inverse of negative 2. You have 2 pi over 3, that's in quadrant 1. Remember, secant is from 0 to pi, excluding pi over 2 with the asymptote, so it needs to be in quadrant 2. Arctangent of root 3 over 3, ignore the theta, it's a typo. 1 over root 3 is the same as root 3 over 3, so we can draw that triangle in quadrant 1. That is where arctangent would be positive. If you were to draw it in quadrant 4, it would be negative. So it has a rotation of pi over 6. And then the last one is negative pi over 4. Tangent inverse, we're restricted to quadrants 1 and quadrants 4. From negative pi over 2 to positive pi over 2. Negative pi over 4 is where we can draw the reference triangle with that ratio of sides of negative 1. So keep in mind, trig functions, radians go in, ratio of sides comes out. When we talk about inverse function, ratio of sides go in, radians come out. Refer to up above for the quadrants you're restricting it to. Sine will always be negative pi over 2 to pi over 2. That's quadrants 1 and quadrants 4. Cosine, quadrants 2 and 3, 0 to pi. Tangent, same as sine. Cotangent, same as cosine. Secant, same as cosine because they are reciprocals. Cosecant, same as sine because they are also reciprocals. I'll clarify any questions that you have tomorrow. You can start your My Math Lab for tonight.